When you're dealing with corrosion in pipework, detection is only half the problem. The real question is, what is the remaining wall thickness? And then one more importantly, can you still trust your sizing method when the pipe condition isn't ideal? My name is John, and today we're going to take a look at MRUT Sizing Axial using InnoSpec Technologies VOLTA 2 system. Now this client, they had a 16-inch carbon steel pipe with a nominal wall thickness of 1/4 inch. But this wasn't a clean sample. The pipe already had generalized internal corrosion and they combined that with 4 artificial defects, including a through-wall hole, a through-wall scratch, and 2 smooth wall reduction areas. And just to make things more interesting, those defects were overlapping both axially and circumferentially. So this isn't a best case scenario. This is much closer to what you'd actually see in the field. Now the inspection method, here in these circumstances, used guided waves generated by a magneto-restrictive strip mounted axially along the pipe. That allows you to scan along the axis while effectively interrogating the full circumference, including areas you can't directly access. Now for sizing, MRUT combines 2 key approaches. Number 1 is amplitude-based sizing using a shear 0 mode and frequency-based sizing using a shear 1 mode. Now in a perfect world, you'd use both. They complement each other and improve confidence in remaining wall thickness estimates. But here is where it gets more interesting. Because of the generalized internal corrosion, the shear 1 mode didn't propagate cleanly around the pipe. And during calibration, channel 2, which carries the shear 1 response, showed a little to no usable signal. So the frequency cutoff method was effectively off the table. Now this is the moment where most techniques start to fall apart because you've just got one of your key sizing inputs, but the inspection didn't stop there. Instead, the assessment relied entirely on the shear 0 amplitude-based method. The strip was positioned about 180 millimeters away from the defect zone, giving a stable baseline in a more nominal section of the pipe. Then calibration was set to the first wraparound signal, and that sat at about 80% screen height with a baseline of about 26 dB. From there, the scan was performed through the defect region. And this is the part worth paying attention to. Despite the degraded condition and loss of shear 1 data, the system still detected all 4 defects, separated them clearly, and even where they overlapped, and produced usable remaining wall thickness estimates. Now let me give you an example. In the overlapping region between defects 3 and 4, the system estimated 30 to 40% remaining wall. Defect 4, which had smooth boundaries and weak reflections, still produced a clear response through wraparound attenuation with around 30% remaining wall. And across the general corrosion areas, remaining wall thickness was estimated at 70 to 80%. Now think about that for a second. Even without the frequency-based sizing method, you're still getting actionable, interpretable data. Now this case study, it highlights something that is easy to miss in theory, but absolutely critical in practice. You won't always get perfect signal conditions. You won't always have every mode available. But if your system and your method is robust enough, you can still extract reliable sizing information from imperfect data. And that's really the value here. So the VOLTA 2 with MRUT Sizing Axial didn't just detect defects. It adapted to the condition, worked within the limitations of the signal, and still delivered meaningful insight into remaining wall thickness. Now, if you're working in real-world corrosion environments, and who's not, that's the difference between interesting data and usable data. My name is John. I'll see you around.